Continuing theorems on open sets in metric spaces. The next theorem is show that the interior set of a subset of a metric space is the largest open set contained in A. So let A be any subset of metric space XD. Suppose this is metric space, this is A, interior will be like this, interior of A. Obviously by definition interior is contained in A. We need to show that A naught, the interior set, is the largest open set which is contained in A. Means there exists no other open set. There exists no other open set B such that B lies in between A naught and A. No such condition holds. That's the theorem. So A be any subset, A naught be the interior of A. If it is empty, that means if A has no interior point, then it will be an open set being an empty set, because empty set is open. So let's take A naught be non-empty. Then A be any element of A naught. If A is in A naught, that means A small a is interior point of set A. We shall show that A is interior point of A naught also. If I want to show A naught is open, I need to show A naught is neighborhood of each of its points. So if I have taken small a in A naught, I need to show A naught is the neighborhood of A. So A lies in the interior of A naught, that we need to show. Now if A belongs to A naught, that means the element A is an interior point of A. And if it is interior point of A, there exists an open sphere with some radius centered on small a. The sphere is contained in A. This is by definition of interior point. We claim that that sphere goes to A naught also. That sphere is contained in A naught also. So with the definition of subsets, we'll take any element from the set SRA. We'll be showing that element belongs to A naught. So I'm taking X belongs to SRA. In the sphere, I'm taking X element. X I'll be showing goes to A naught. Then A naught will be neighborhood of A. So X belongs to SRA and every open sphere is an open set. So it has to be neighborhood of each of its points. It has to be neighborhood of X here. So this implies there exists an open sphere centered at X with some radius, and that sphere is contained in SRA. This implies SR1X is a subset of A using this equation, name it as 1. So using 1, I can say SR1X is subset of A, and which implies X is an interior point of A. This implies X belongs to A naught. Hence, the sphere SRA is a subset of A naught. Thus, A is an open set, as every point of A naught is its interior point. A naught is an open set, as every point of A naught is in its interior point. Still we need to show it is largest such set which is contained in A. See, containment is by definition. Open set we have proved. Largest we need to prove. So we have proved A naught is an open set. Also by definition of A naught is contained in A. So A naught is an open set contained in A. Now to prove the result, it remains to show that A naught is largest open set contained in A. For this, let B be another open set contained in A. Let B be another open set contained in A. So this implies B is subset of A. Now we need to show B is contained in A naught, means A naught is largest. We have taken any set B which is also open and contained in A. We'll be proving A naught is superset of that set. That means A naught will be the largest one. So let X belongs to B, any element. There exists an open set. There exists an open sphere with some radius centered at X that will be contained in B by definition of open set, as B is open set. So now sphere is contained in B, B is contained in A. That simply means sphere is contained in A, which simply means X is an interior of A. That is, X belongs to A naught. So X was any element of set B. We have proved it is also in A naught. So B is a subset of A naught. Hence A naught is the largest open set which is contained in A. There is no set larger than A naught which will be open also and contained in A also. Next result, in a metric space XD, A is open if and only if A naught is A. Let A be any subset of metric space XD. By definition of A naught, interior can also be defined as, by definition of A naught, we can write interior of A as union of open spheres, and the spheres are contained in A. And also every open sphere is an open set. Every open sphere is an open set. And we have also proved arbitrary union of open sets is also open. So this implies A naught is open set always. This we have proved in previous result also. A naught is an open set. So this was another way of proving also. Now also A naught is the largest open set contained in A. This we'll be using from previous result. So first of all, I am assuming A naught is equals to A. If A naught is equals to A and A is an open set, as A naught is an open set, because we have proved A naught is open set and A naught is equals to A, that means A is also open. Conversely, if you take A is open to prove A naught is equals to A naught is subset of A by definition. To prove the reverse criteria, A is a subset of A, we can say, because A here is open. We have assumed A as open set and every set is contained in itself. So A is a subset of A, but A naught is largest open set contained in A. So A naught must be greater than A. A naught must be superset of A. And by equation 1 and 2 we have equality. So we have proved this result both ways. If A is open, A naught is equals to A, and if A naught is equals to A is open.